the very kind invitation. Moire patterns can be produced not only by twist, but also by layer mismatch between layers of atoms that can be metals, can be semiconductors, can be magnets. And many things can happen. We can stack homo layers, hetero layer. We can have stack layers of different nature between them. Effects from one layer can be inherited in the other layer. That happens in magnetic system. For instance, you can get the whole system magnetic, even so the two layers were not at the beginning, just by twisting. And these kind of moire patterns, we can, not me, but people in the lab can make them just applying strain, applying pressure, twisting, but also in nature, sometimes materials crystallize in different ways. For instance, in these crystals, they can be rhomboedral or monoclinic phases, and they produce different type of phases, skyrmions in one case, of some different nature than in the other. In this case, for instance, in this magnet, where magnetic atoms lie in the honeycomb lattice, when you have many layers, this is a van der Waals material, the system crystallizes in one way. That means that the sulfur atoms are going to be located in some tetrahedral arrangement, but as you exfoliate the systems and you go when up to 2 layers or 1 layer, the arrangement of these sulfur atoms change, and because of that, the magnetic properties of the system change, because the d orbitals that are active under those conditions are different than the ones that are active for the bulk material. So even so, we can produce this lattice mismatch of moire and give rise to moire patterns artificially. Also, one can think that perhaps they exist also in nature in a natural manner. Broken symmetry that arise in many cases is the periodic arrangement of the charge in this type of systems. So this is the a periodic arrangement of a charge, which is characterized by an amplitude, a wave vector, and by a phase. You can find that the wave vector is very sensitive to these moire patterns. So here, the out-of-plane momentum dependence of the charge density wave can be changed in these systems depending on the arrangement. In this case, there are chiral type of charge density wave, so that the intensity peaks of the charge density waves decrease clockwise and anti-clockwise. Also is sensitive to that. Also, they can happen in many systems, and for instance, can be modulated by doping, like in this case. So, whole doping here leads to the suppression of the charge density wave transition temperature and the emergence of actually an uncommensurate charge density wave, where the periodicity of the charge is not an integer number of the periodicity of the lattice. Yeah, here there are other examples. 3Q state, which is the lowest energy configuration in the unstrained case, but a little uniaxial strain actually break that symmetry to 1Q, and this is other case where depending on temperature you can have like one type of individual charge density wave arrangement, but in some intermediate state you can have a composite type of order. And here, well, the moire situations, many cases. This is the paper of Hector, which I pay a lot of attention. So you can have moire system where you have the two lattices can have a charge density wave, and you twist them, and then the charge density arrangement change. Or you can have system which don't have any charge density wave from the start, and then you twist them, and actually the charge decide to arrange in some pattern. So usually the traditional way how to understand the charge density way phase is starting from a one-dimensional system which somehow is dimerized, and with this dimerization actually the band open a gap, and that state actually lower the whole energy of the system. So this is a typical Hamiltonian, Froelich Hamiltonian, where we have like creation and annihilation operators for the fermions, for the electrons. Here we have the frequency of the normal phonon modes. These are the creation and annihilation operators of the phonons. And here is the interaction, the coupling between electrons and phonons, which is given by this J sub Q. Essentially, you know, the static the static displacement of phonon of the systems give rise to a potential, and this potential actually change produces strain energy in the lattice, and that also change the energy of the band, and the competence between these two is going to set the critical value for which this pure transition happens. And essentially, the key condition for this pre-transition and the subsequent charge density wave formation is a Fermi surface instability, and that is what is called Fermi surface nesting. And this is a very interesting paper, actually, where Massin and company actually explain why those conditions where this perfect nesting are actually very, very difficult to accomplish in nature. Okay, so this is a toy model which I would like to try to understand. So I will consider two systems. Okay. The name of the first system is bond ladder. The name of the second system is side ladder. So here I have a chain of two atoms, the white and black. Okay, and below I have another chain with atoms white and black. Okay, which has a slightly different lattice constant. Okay, so the distance between the black here is 2a delta, and the distance between the black here is 2a. So let's set a equal to 1, and delta is a rational number very close to 1. Okay, so I will consider, to start with, hooping between nearest neighbor sites and interlayer hooping. So this is this system. The other one, the top chain is exactly the same as this one, but the bottom chain is slightly dimerized. That means that the distance between the white and black here is going to be a little smaller than the distance between the white and the black to the left. All right, so this is the distance in terms of delta. Okay, and so this is one distance, this is the other. Okay, again, hooping among the two chains and intra-chain hooping. All right, so this is the Hamiltonian for the bond ladder system, right? So it's just hooping at nearest neighbor level in the same chain and inter-chain hooping. Okay, and the hooping here is the same. Okay, left and right. In this other case, we have that because, you know, the distance between left and right in the second system is different, given by delta. The hooping is going to acquire a phase, which is in terms of delta. Okay, so you can write, this is a 4-band model. Okay, so this is just the Hamiltonian of the bond ladder. Okay, we set our T perpendicular divided by T parallel equal to T, A equal 1, Okay, so this is the Hamiltonian, this is the spectra, okay. And for this one, almost the same, but the phase there, this is bottom chain, top chain, again, same thing. Again, the spectra, okay. Eigenvectors in both cases depend on delta, okay. So I just diagonalize that Hamiltonian, both of them. So this is what happened for the bond ladder. So delta equal 1, which is the trivial case, right? So we have the two bands here, the other two there. Okay, this is the density of states with the Van-Hoff singularities due to the top and bottom of the energy, and these are the other two due to these flat bands here and there. And then delta equal to 0.95. Okay, the system remain a metal, but these two Van-Hoff singularities, they go lower, so there are less states available, okay, and this is what happens when you change delta. So just to remind you, the moire period in this case, in case you haven't read the paper of Calaf and company, is going to be 2 pi divided by 1 minus delta, right? So the number of sites in the unit cells increase. So this is the moire period. This is when these patterns essentially repeat, in this new system, right? This is the other case. This is the side ladder. This is the one that has the bottom chain dimerized. All right. So now a gap open. All right. So this is almost 0, not 0, because one have to put some delta in Mathematica for things not to get infinite, right? So there is a little gap here. So the system now becomes an insulator, okay? And we see the splitting in the density of states, due to these new Van-Hoff singularities that will arise. So these two systems essentially have the same periodicity. Everything is the same, but in one of them, it remains a metal. The other one becomes an insulator. So we have a small parameter now, which is 1 minus delta. Let's call that epsilon. Okay, so we can expand the energy, okay, the band energy in terms of epsilon. We can compute the stationary points of the moire bands. Okay, so for that we have the group velocity. Okay, the group velocity can be greatly expanded, as the energy was, okay, and then we make the group velocity equal to 0, and with that we can find essentially delta in terms of k, and for this k at a given delta, those k's for which the energy is 0, which is where the chemical potential is, essentially Van-Hoff singularities will arise. Okay, so those delta that are here, okay, which can be approximated in this manner, essentially are delta are quadratic with k, will show charge features in both the density of states and also in the susceptibility. Okay, which suggests that the system could have around those points perhaps charge density wave instability. So let's start by looking at the linear electron response function. So one can compute the whole thing, but we can again expand the energy at first order and just also expand, this overlapping, and just plot this part to start with. And we see that, of course, the peaks, coincide with the moire periodicity of the systems, but there are little wiggles here. Okay. So we can just compute the charge density in the system. So this is the Fermi energy. This is just the wave functions, okay, square. And this is the case for the bond ladder, okay, for a given delta. This is for delta equals 0.8. This is for delta equals 0.95. Both have the bond ladder and the side ladder have the same T. Remember, T was T perpendicular divided by T parallel. So all in units of T parallel, if you want. Chemical potential is 0 at the same temperature. And of course, the large peak here coincide with the moire periodicity. But there are other harmonics. Okay, these lower peaks actually are product of the periodicities of the individual chains. Right, so these big peaks in both systems, bond ladder and side ladder, correspond to the moire supercell, and the small peaks are combination of the moire pattern and the individual chains. Okay, both in this case is asymmetric. This is because in one case we can say we have a moire potential, which is kind of a cosine, is symmetric both way, and the second system we break inversion symmetry, so we expect that these patterns are going to be, they don't have to be, there is no reason why they have to be essentially the same size at both sides of the central peak. Okay, so the eigenstate are block wave in a lattice whose reciprocal vectors are those of the individual chains and that of the moire supercell. So at first order, so the wave function can be seen like in this manner, where this Cm is like proportional to the moire pattern, where in the bond ladder can be approximated like that, and this is just something that is anti-symmetric. Okay, so the density Fourier components, okay, of the charge density at this level, not interacting level, they come from these cross terms here, in such a way that the wave vector of the non-interacting system of this charge density waves are going to be first the moire supercell wave vector plus, you know, this primitive vectors of the individual chains. Okay, so this will determine these satellite peaks in the charge density wave. Okay. All right, so let's see if actually happens when we add interactions. So same system. Now I will name this chain the upper chain A. Before didn't have a name. Now the bottom chain I will call it B, and I will also name the sides just to keep track of what I'm talking about. So black side up 1, white side 2. In the B chain, the black one is 3, and in the B chain, the white side is 4. All right. Again, intra hooping in the same chain, inter hooping between the chains. Okay, and I will have a Coulomb interaction between nearest neighbor chains of the same size, a constant, not Q dependent. Yes, U. Okay, so these interact just by this short range Coulomb potential. And the same story in the side ladder. Okay, so the only change in notation is that I put numbers to my sides and I put letters to the chains. Okay, and this is the type of interactions that I have. So this is my kinetic Hamiltonian, which is diagonalized by U matrix, in which columns are the eigenvectors, okay, belonging to these eigenvalues. All right, and I have my operator, which I can change basis with the band operator. So I go to the band basis, which is the band, I mean what diagonalize the kinetic Hamiltonian. And I can also define chain projector density vertices in the band basis, which are going to be given by this density here. So X is A or B, and these gamma are going to be the form factors, if you want. This U, remember, is the matrix of the eigenvectors of the non-interacting Hamiltonian. Okay, and the L denotes the site, which in the chain A they are 1 and 2, and in chain B L are 3 and 4. So only in the same chain interaction constant U. Okay, so this is the interacting Hamiltonian then written in this way. Okay, so yeah. So let's try to do a mean field decoupling to get rid of these quartic terms in the operators. So for that, we can write the grand canonical action in imaginary time. So this is the kinetic part, right? And this we have here the interacting part. And then we can use a Hubbard-Stratonovich transformation and introduce bosonic Hubbard-Stratonovich field phi sub x, where x is A and B, the level of the chains. And with that, we can express our partition function and in this manner, okay? And then we can also decouple and retain only terms up to with q, small q equal to plus and minus big Q, take complex ordered parameter and use the saddle point approximation in which my ordered parameter is stationary. And for that, when I do that, I get to the matrix gap equation. Okay, which is useful because using that I can get like a more precise susceptibility. So usually for doing that, one consider only band diagonal densities. So the n here in this band operator and here are the same. This is why this is diagonal. We can define exactly the kernel because we know the eigenvectors of the non-interacting system. So the kernel is defined in terms of these eigenvectors. And then again, the interacting action, apply the Hubbard-Stratonovich transformation and the saddle point, and finally we'll get to this condition for the density wave instability, where our original susceptibility, the previous one, just have is multiplied by this matrix V, which contains the U, and multiplied by the form factors now. So the overlap between the wave vectors, the wave function is considered in this way. Okay, so and the typical thing that one does is essentially find the maximum eigenvalue of this matrix and identify the Q for that eigenvalue is equal to 1, and that Q will give us which is the critical, the wave vector of this charge density wave when such interactions are present in the system. Okay, and also beside this Q, let's call it Q asterisk, we can get also the critical interaction, okay, for which this instability will appear, or also one can get, scanning for temperatures, the critical temperature. So this is how, this is just playing a bit with delta equals 0.95 and temperature 0.01, and chemical potential is 0 in both cases. And one can start playing for different delta and play a little bit with scaling, and essentially what one get is that the Q of the charge density wave is going to be delta divided by 1 minus delta multiplied by pi. So smaller than what the non-interacting susceptibility predict, because it's multiplied by a rational number multiplied by the moire lattice constant in the system. This is an incommensurate charge density wave. One can check that as delta increase, the critical interaction decrease and the critical temperature increase in the system. Okay, and what is also interesting is that the critical interaction for the bond ladder is smaller than for the side ladder. So in this system now we can select. This also gives you the channels where this eigenvalue is going to be maximum. So we can now focus in 2 bands, all right, N and M, and this is going to be the grade the form factor in terms also for Q asterisk and this after the typical Hoover-Stratanovich again for this special dominant bands M and N, and for this Q asterisk allows to write the subtle approximation for the Lagrangian of the system. Okay, so this is and from this Lagrangian one can get the Hamiltonian. This is the mean field Hamiltonian. The spectra of that mean field Hamiltonian gives the quasi-particles for of the system. Okay, as we have a metal in the bond ladder, those quasi-particles are just holes and electrons. Like in the case of the gap system, which is the side ladder, those quasi-particles should be like excitons. Okay, which are live in K and K plus Q asterisk, where Q asterisk is where the charge density states arise. Having the mean field Hamiltonian, we have the quasi-particles in the systems are excitons in the side ladder, are electrons, are holes in the bond ladder. The collective excitations are going to be essentially the phase of those charge density waves and the amplitudes of those charge density waves. So we can write the order parameter in this way, where here is the phase, and we can include the phase into this Lagrangian just using an axial gauge rotation and using the minimal coupling. We incorporate this theta inside the main field, right? And we have then the Phasons, okay, action where Phasons because of phase, because of the theta. So so with this action of the Phasons or of the phase, one can variate this action, and from variation of it, one can find the equation of motion for the phase, okay, in the system. And this is the equation of motion, and essentially that gives you that the Phasons is a Goldstone mode because it has a linear dispersion with Q. Okay, yeah. It's incommensurate. It will slide free. It will slide freely, but it is incommensurate. Incommensurate. So it won't. It breaks symmetry. This is a Goldstone mode, right? So it will break a symmetry. The symmetry that breaks is translational symmetry. That means that it won't. It cannot move anywhere in the lattice, but it will go to some specific places where incommensurate because the Q is proportional to delta, and delta is a rational number. It's delta essentially multiplied by the periodicity of the moire lattice. So one can also get some idea of how this Phasons is going to behave. So near this hot spot is where this K and K plus Q asterisk, they touch. People call this hot spot. So this the Phasons is characterized by a static stiffness. This is what kappa is. This is dynamic stiffness, essentially the inertia of the Phasons. And this rho is the static stiffness. That means how much energy, how much it costs to rotate these states. So kappa and delta, they define together the velocity of the square root of rho divided by kappa, define the speed of the Phasons, the velocity of the Phasons. So near this hot spot with bands N and M, coupled by this charge density wave at Q asterisk, one have that this kappa actually scale like the density of state of the system multiplied by the form factor. Remember, this F is just this multiplication of this coefficient of the U matrix, which is the eigenvectors of the non-interacting system. Because the density of state is inversely proportional to the Fermi velocity, we have that kappa should be proportional to this form factor square. Here is delta enclosed and divided by the Fermi velocity. For the case of rho, the static stiffness of the Phazon, it should be proportional to the density of state and also the form factor, okay, and the relative velocity between these the hotspots. So essentially proportional to the Fermi velocity and proportional to the form factor square. So what actually happened? So there is two energy scales essentially. So it's T, the interlayer coupling, and it's delta, which gives the moire type of potential. So T, the interlayer coupling, or widen the moire tie-binding mini bands, okay, increase the Fermi velocity at the hotspot, and reduce the same chain weight in F, okay. So essentially, again, stay delocalized across the chain because of the body. So rho, the static stiffness, increase because the Fermi velocity grows, and the Phazon velocity as a consequence of that is going to increase, okay, linearly with the Fermi velocity as T, the interlayer coupling, increases. As delta actually approach 1, the minimums flatten and the nesting sharpens. And what happens, of course, the Fermi velocity decreases because of the flatter bands, and the static stiffness is going to increase because there is a bigger density of states, and then the rho is going to go smaller because of it's going to be a smaller Fermi velocity. In the mini band, the width scale like 1 minus delta, where delta again is this moire kind of pattern. So the static stiffness scales like the structure factor divided by the bandwidth. That's going to give us that is going to be inversely proportional to 1 minus delta. While the static stiffness, this static stiffness is going to be proportional to the form factor and to the width of the mini band. That means that it's 1 minus delta, scale like 1, which means that the Phazon velocity is proportional to the bandwidth. It's going to be proportional essentially to -1 minus delta. So turning up the interlayer hooping, speed up the Phazon, and pushing delta to 1, slow down the Phazon. And with that, I thank you very much.
So did you look at what happens when the electrons now interact with these phasons? Because you have one phase that is metallic, right?
Yeah, I have the two phases. In one case, it's metallic, and remain metallic, well, at least until the charge density wave appear, right?
Oh, but then it becomes insulated in the CW phase.
Yeah, because a gap will open, yeah.
Okay, so then there's not much. And I don't remember, is it the case that when this phason should become gapped once you include the long-range Coulomb interaction?
I don't know, Rafael, maybe, perhaps, well, that's the next.
Okay.
But in which case would you include the long-range interactions?
I'm trying to remember the story that if you have an incommensurate CDW and then you have the phasons, they're gapless, but if you include long-range Coulomb, it opens a gap, becomes the plasma.
Fukuyama ligap.
Yes, thank you.
Yeah, I haven't read. Okay, Fukuyama. Okay, I'll take a look.
I am sorry if I have missed that part, but when you're solving the eigenvalue equation, this is a linearized eigenvalue problem. Yeah. So then you were determining which of the two phases wins based on the maximum eigenvalue, right?
I mean, you find so you have this 2x2 matrix, right?
Yes.
And then you find the maximum eigenvalue that serves to you. You find then you identify the Q asterisk. That's what you do.
So it's not that you are finding the TC where you have an eigenvalue equal to 1?
Yeah, you can also use it to find the TC, right?
I see. Okay.
Yeah.
All right.
More questions?
So, Paula, quick question. So, you have these one-dimensional systems.
Quasi-1.
Yeah. So
I have to say quasi-1 because interaction across chains are important, and I know that one-dimensional one, bad things can happen.
right. But so if I were to look at the limited one-dimensional systems, and if I were to include spins, do you have any things that spins would play a role?
But if you just have one-dimensional system and then you include the spins, you will have this charge spin separation or
right.
So
that's exactly what I'm trying to bring here. So in your case, what happens when you start coupling those?
Well, the chains are coupled all the time here. If I turn off the coupling, I don't get charge density wave. I mean, I just have to separate the chains. And you have
spin degrees of freedom that you're considering or not?
No, I haven't. Yeah, I haven't included spins.
It's completely
spinless systems. Yes.
Right. So the question is then, what would happen if you have?
I have no clue. Yeah, but that's the next step, of course. Just couple the spin magic. So yeah.
Thanks for your talk. So I'm wondering how exactly, if you have any ideas of how these results would generalize, for example, in 2D. Because in 2D, in principle, one could have a CDW without fully gapping the system, right? Like nothing could be incommensurate and still having some conduction electrons. So do you think that your conclusions are robust against this case, for example?
I don't know. That's a good question.
Thank you.
No more questions? So we thank Paula again. Yeah, and Rafael has